Good morning, students. Once again, I welcome you all to another video lesson from the chapter Work and Energy. Today, we shall be discussing about the law of conservation of energy. What is law of conservation of energy? According to the law of conservation of energy, the total mechanical energy, that is, the sum of kinetic energy and potential energy, remains constant in an isolated system. Now, you might be wondering, what is an isolated system? A system comprising of at least two objects in which no external forces are acting. That type of a system is called an isolated system. Only the objects that make up that system are allowed to interact with each other. So for that type of a system, the total mechanical energy, that is the sum total of kinetic and potential energy, will always remain constant. The energy in a system can neither be created nor destroyed. It can simply change from one form into another. According to this principle, in general, total energy remains constant in a system. Now, let us make it clear with the help of few examples. First of all, we shall consider the example of a freely falling object. For that, I will take help of a very simple diagram. Let me mark the initial position and then an intermediate position and then the final position. Let these positions be A, B and C. So let the height from A to C be equal to h. Now, if from A to B the height is x, then obviously from B to C the height will be h minus x. So we shall make use of this very simple diagram. Let the object be in the form of a ball that is taken from A to C. So initially the ball is at this particular position and then it falls down to C. Let the mass of the ball be m. So let a ball of mass m fall under the effect of gravity alone from point A at a height h above the ground. Then let me consider the first position, that is for position A. The ball is at rest, so its velocity is 0. Then kinetic energy will be equal to half mv square, that will be equal to 0. And what about potential energy? Potential energy will be equal to mgh. So total energy, that will be equal to kinetic energy plus potential energy, that shall be equal to 0 plus mgh. So obviously this is equal to mgh. Now let's consider the next position. Position B. Now let us go back to the previous diagram. For position B, the object has fallen through a height x, it has fallen through a distance x, and now it is at a height h minus x from the ground level. So now, if v is the velocity of the ball at B, then we get v square minus u square equal to 2as. So substituting the values, we get v square minus 0 to be equal to 2gx. That further implies v square is equal to 2gx. This means kinetic energy, that shall be equal to half mv square, and this is equal to half m, and v square is equal to 2gx. So 2 and 2 shall get cancelled, and we are left with mgx. Potential energy. Now the object is at a height of h minus x from the ground. So mg h minus x, that shall be the potential energy. Let us solve it further. So this becomes mgh minus mgx. Therefore, total energy, that is equal to kinetic energy plus potential energy, that shall be equal to mgx, which is kinetic energy, plus potential energy, that is mgh minus mgx. So these two terms get cancelled out, and so once again the total energy becomes mgh. Now once again let me go back to the previous figure. Now we shall consider position C. So for position C, now the object has travelled through a distance h while moving from A to C. So if v is the velocity of the ball just before it touches the ground, if v is the velocity of the ball just before it touches the ground at C, then again, since v square minus u square is equal to 2as, so on substituting the values, we get v square minus 0 to be equal to 2gh. That gives us v square equal to 2gh. So now kinetic energy will be half mv square, that is equal to half into m, and v square is 2gh. 2 and 2 get cancelled, and we get kinetic energy as mgh. Potential energy. Potential energy will be equal to 0 since the object has reached the ground level. Therefore, total energy, that is equal to kinetic energy plus potential energy. So that shall be equal to mgh plus 0, that gives us mgh. So now let me show you the total energy at position A, that is equal to mgh. For position B it is equal to mgh, and for position C it is equal to mgh. This means that it is quite clear the total mechanical energy, that is the sum of potential energy and kinetic energy of a freely falling ball or a freely falling object, remains constant in all situations. Now, suppose I want to give a graphical representation of this situation. For that, I will draw the axes. So on one direction I've got total energy. I'm plotting energy actually, so it will be total energy, potential energy as well as kinetic energy, and on the x-axis I will be plotting the height. This is the origin. So it is found that the graph for kinetic energy becomes like this. So this is the graph for kinetic energy. Now let me show you the graph for potential energy. So the graph for potential energy is like this. And what about total energy? The graph for total energy is, just a minute, the graph for total energy is like this. So this is how the variation of mechanical energy, both kinetic and potential, with height can be shown graphically. The total mechanical energy of the falling ball remains constant. Let us consider one more example, that of a swinging pendulum. Let a pendulum be suspended from point O. Let P1 and P2 be the extreme positions of this pendulum and M be its mean position. Now, the bob is at rest for a moment and its energy is entirely potential at both the extreme positions. So, we can write down for position P2 potential energy, that shall be equal to mgh, where h is the height of position P2 above the mean position m. Now since the bob is at rest at P2, therefore its kinetic energy at P2 itself is 0. As the bob moves from P1 to O, its potential energy changes into kinetic energy. It moves from the extreme positions to the mean position. Its potential energy changes into kinetic energy. So, if we assume that at the mean position v is the velocity, then kinetic energy at m, this shall be equal to the potential energy at P1. Now, if v is the velocity at m, that is the mean position, then kinetic energy will be equal to half m v square. So we can say that potential energy at P2 has been converted into kinetic energy at m. A swinging pendulum has potential energy at the extreme positions and kinetic energy at the mean position. So for P2 the energy is potential, for M the energy is kinetic, and for P1 again the extreme position energy is purely potential in nature. Let us now study about an important term in this lesson, that is power. Power is defined as the rate of doing work. It is measured at any instant as the product of force and velocity. Fastness or slowness of work done by an object is given by the power of that object. Now, mathematically, power at any instant is given by P equal to W by T, that is work done by time. Now, as work done is equal to force into displacement, so this implies power is equal to force into displacement by time. Now displacement by time is velocity, so we get power to be equal to force into velocity. So these are the two different expressions for power. Now practically, an object may do work at different time rates at different intervals of time. So, total energy consumed divided by the total time taken is called average power. Total energy consumed divided by total time taken is called average power. Let us take an example. Compare two different types of two-wheelers, say one a moped and another a motorcycle. Let both be given the same work, say carrying a bag of cement uphill. Which of the two you think will do this work quickly? The answer will be, of course, the motorcycle. So we can say that motorcycle is more powerful. Similarly, in the picture you can see a crane. They lift very heavy objects and so quickly. So we can say that they are very powerful. This means a measurement of power is done on the basis of how much work is done in how much time. SI unit of power. SI unit of power is joule per second. Since formula for power is work by time, unit for work is joule and unit of time, as we all know, is second. So obviously from the formula we get the SI unit of power to be joule per second, and it is called watt. So SI unit of power is watt. Now the unit of power is named after physicist James Watt. The power is said to be 1 watt if an object can do 1 joule of work in 1 second. Another unit of power is kilowatt, denoted by kW, and 1 kilowatt is equal to 10 to the power 3 watt, that is 10 to the power 3 joule per second. Now, power of a motor or an engine is generally given in horsepower, and it is written as HP. Now, how much is 1 HP equal to? 1 HP is equal to 746 watt. So, this is also another very common unit of power. So, this brings us to an end of our discussions from the chapter Work, Power and Energy. Thank you.